Modern automated systems operate under a severe constraint. They must make definitive, high-stakes decisions using fragmented and noisy data. When an autonomous machine navigates a chaotic physical environment, it cannot rely on perfect information. The unpredictability of physical reality guarantees that sensors will be flooded with interference. Consider an air defense radar tracking a blurry, intermittent blip on the horizon. The system is immediately forced into a classification crisis, required to categorize an object it can barely see. A fiber optic receiver sorting through a barrage of electromagnetic static to interpret a stream of light pulses faces the same structural problem. And a network firewall parsing millions of seemingly normal data packets for a hidden targeted intrusion shares this identical challenge. These disparate engineering challenges are all governed by a single mathematical framework formulated in the 17th century. That framework is Bayes' theorem. It functions as a universal engine for reverse probability. Bayes' theorem provides the mathematical mechanism that allows modern technology to statistically map observed effects back to their root causes. To see how this engine works, we have to move from the physical world into abstract mathematical space, beginning with a total sample space that contains all possible events. Conditional probability functions as a structural restriction of reality based on a known event. This diagram represents a complete sample space. Confirming that event F has occurred acts as a boundary, shrinking the universe of possibility down to F. To calculate event E, the math occurs exclusively within the intersection where E overlaps with our newly restricted reality, F. If two events are strictly independent, their probabilities scale linearly. But for dependent events, the multiplication rule relies on this restricted conditional state to remain accurate. Bayes' theorem partitions the sample space into mutually exclusive events, creating a precise equation. First is the prior probability, the baseline state. Next is the likelihood, the probability of seeing evidence if a state is true. Together, they form the posterior probability, the updated reality. By updating baseline assumptions with new conditional evidence, the theorem creates a dynamic model that continuously refines its own accuracy. We can apply this structural logic to the macro scale of aerospace engineering, specifically the problem of sensor fusion. Imagine an air defense radar detects an unknown inbound object. In Bayesian terms, this detection is the observed effect, or event A. The system must partition the sample space into three causes, either a commercial airliner, a flock of birds, or a hostile missile. Before the radar even pinged the object, the system established the prior probability based on historical flight corridor data. As the object approaches, the radar records a specific radar cross-section, or RCS. This is the new physical evidence. The system uses this RCS signature as the likelihood term. What is the probability of seeing this signature if the target is a bird versus a plane versus a missile? It uses that answer to update the probabilities across all three causes. With every new radar pulse that returns, the equation runs again. The system continuously recalculates the posterior probability, refining its certainty with every microsecond of data. This Bayesian updating quantifies doubt mathematically. It ensures the system relies on cumulative evidence, preventing false alarms or delayed interceptions. The exact same Bayesian variables map onto the microscale of digital telecommunications and fiber optics. In any transmission, energy waves distort and fracture as they travel through a highly chaotic, turbulent atmospheric medium. This creates the problem of bit error rate. Because of electromagnetic interference and thermal noise, a 0 bit transmitted by the source might be received as a 1. We establish our discrete Bayesian events. The prior event is the act of transmitting a 1, and the observed effect is the system receiving a 1. The receiver's logic holds a known channel noise profile, the baseline rate of interference. This noise profile acts as the likelihood probability. Look at this binary data stream. When a 0 flickers into a 1, the equation uses the channel noise profile to calculate the probability that the original bit was actually a 1, factoring out the noise. Without reverse probability, modern digital communication would rapidly degrade into static. Bayes ensures high-fidelity data reconstruction across degraded channels. We can scale this logic further by moving from physical signals to computational software architecture, specifically machine learning and cybersecurity. Spam filters and intrusion detection systems share a sorting challenge, isolating tiny malicious payloads hitting within vast volumes of network traffic. In this domain, the prior probability is the known baseline rate of malicious traffic hitting a specific network. The likelihood trigger occurs when the algorithm detects a specific keyword or payload string inside a packet, such as the phrase unauthorized access. Using a naive Bayes classifier, the filter calculates the posterior probability that the packet is malicious, based on the presence of that keyword. This network diagram illustrates the engine's scaling mechanism. Rather than checking one word, it multiplies the conditional probabilities of hundreds of independent keywords simultaneously. Once that multiplied posterior probability crosses a specific mathematical threshold, it triggers the system to instantly drop the malicious packet. By layering Bayesian logic, software transcends simple rule-based firewalls. It creates dynamic security architectures that probabilistically map out complex threat landscapes in real time. We can validate this structural logic through a high-volume manufacturing simulation. Tracking manufacturing defects within a factory system, we have industrial robotic arms moving down an endless manufacturing assembly line, processing materials in sequence. The system variables are set to 3 distinct assembly lines. Each operates at a different speed, and each has a unique known error rate. The critical incident occurs when a single defective part rolls off the line. This is our observed effect. The mathematical objective is to determine the probability that a specific assembly line produced this exact defective part, rather than the other two. This split screen places theory directly against empirical data. On the right, the calculation from Bayes' theorem. On the left, tracking raw simulated physical output. We run millions of iterations, producing a live distribution of defects. Early on, the data fluctuates, but as the volume scales, we reach a moment of convergence. The brute force empirical data aligns with the reverse probability calculated by the equation. The alignment between millions of simulated iterations and the Bayesian equation confirms that reverse probability accurately models the distribution of physical events.